overview of the switched reluctance motor. Let's see how far we are able to proceed. So we will try to discuss switched reluctance motor here. Actually, first we will try to go with the historical context. So what's actually happened in the previous year. So somewhere in 1830s, so early development has been done, and with the emerging of power electronics and digital control system, nowadays switched reluctance motors have been widely used, and mainly because of the advancement of this electric vehicles here, the switched reluctance motor has been used. And if I want to tell you this advantages of advantages for electric vehicles here, it's mainly because of less expensive compared to the other vehicles here. It's because of less expensive, that's why it is majorly preferred. And coming to the reliability, so here, as we are not using any permanent magnets here, so there is less chance of demagnetization here. There is less chance of demagnetization, whereas we'll actually get into this once we enter into the unit here. So here control simplicity is is easy here because of the inherent characteristics of the circuit here, and it has very high efficiency. And this is also one of the main reasons nowadays in selecting the motors in EV here. Coming to the major challenges here, here as it is inherent nature of switched reluctance motor, it leads to torque fluctuations here. It is the major drawback here. So it is leading to the vibrations and other things here. Okay. So when I use any motor and which is leading to the torque fluctuations, and when it's causing vibrations, it is difficulty a drawback, even if I'm using in vehicles or anything here. Non-linear it is here. So as magnetic behavior is non-linear and complex here, so precise control and modeling will be challenging here. This is also one of the drawback here. And when I'm using the different torque ripples is more, so the sound generated will be more here, and this is also one of the major limitation here. And coming to this, let's actually get into the topic here. So yeah, let's once again try to discuss the strengths and drawbacks here. So coming to the strengths here, it is simple in construction because they don't have any permanent magnets here, and high speed, it can be used for high speed applications here. And it is major advantages suitable for in-wheel drives here. That means, so here in wheels directly I can able to place this motor here. So there is no separate need of this any mechanical gear and other things here. So that is a major, and directly I can keep this motor into the in-wheel here. And coming to the drawbacks here, as we discussed that here, lower torque density. That is torque density is nothing but torque per unit volume here. So amount of power or torque generated will be decided by this torque density here. So here the torque density is less. Okay, with the same weight or the same torque density, is the other machines can able to generate more amount of power here. And we already discussed that the torque ripple is more here, and the noise also more here. So it has certain advantages as well as certain drawbacks here. We'll actually get into this in detail of the unit here, that is structure of the switched reluctance motor here. So coming to the structure means it is construction here. Okay, it is construction here. So doubly salient type rotor here. That means it has both stator as well as rotor has salient poles here. You can see the diagram here. So this is the yellow one is the rotor, and pink one is the stator here. It specifies it is stator, and this is rotor here, and this short one here. And these are all the common parameters that we normally use in any machine here. So here in both the stator as well as rotor here, the type is it is in salient type here. So that is projecting poles will be there, like we also say that it is teeth here. And one more characteristic is that no rotor windings or permanent magnets. As we already discussed that there are no permanent magnets here, so that there is no effect of demagnetization. And similarly windings also not there in the rotor here. So that is, when there is no windings here, the rotor switcher is simplified, and it reduces the manufacturing complexity here. And coming to the one more thing here, concentrated windings here. Stator windings are completely concentrated here, so that again the constructional process is made very easy here. It's easy to design here. Okay, and and topological variations is nothing but here we can able to decide the number of phases, number of stator poles and number of rotor poles. It will affects the machine performance here. Okay, so sometimes it may be 6x4 and 8x4. We'll try to see that actually. Okay, so this is actually the corresponding diagram here where the end one is short and this is rotor, this is stator, and both the stator and rotor are salient type. And this is also salient type here. Common topologies. What are the normal topologies that we use here? That means number of poles in the rotor as well as number of poles in the stator here. That is 3 phase 6x4 pole here. That means here I am using 6 poles. Okay, here I am using 6 poles here. 1, 2, 3, 4, 5. So that is 3 pole pair. 3 pole pair. Okay, that is into 2. That is equal to 6 poles. That is equal to 6 poles here, and 4 rotor poles and 6 stator poles here. When we combination that we call it as 6x4. And what the advantage here? It is lower cost here, better phase advancing capacity, and coming to the disadvantage here, higher torque ripple here, and noise is also increased here. And there is one more other combination is also there. That is 8x6 here. What are the advantages here? That means 8 poles in the stator and 6 poles in the rotor here. The advantages are we can able to generate the starting torque, improved starting torque, and low torque ripple is comparatively reduced here. And coming to the disadvantage here, higher converter cost here. Converter cost is increasing here because of there are more number of poles are there. So each time I need to energize and energize each pole separately here, so that converter cost is increasing here. And let's try to consolidate it here in terms of multi-tooth here. That means if I have more than 2, then I can say the multi-tooth here. So by increasing the number of poles here, just now we have discussed 6x4 and 8x6 here. Okay, combination where this first one stands for stator and second one stands for rotor here. So here in general, by increasing the number of teeth per stator pole can theoretically increase the torque density. And this is what we discussed. The torque density previously it was said that it is torque density is in the SR motor torque density is less here. Now here by increasing the stator poles, torque density can be improved here. So what are the practical limitations here? So winding area is reduced here. So decreased inductance difference here. That is between the aligned and unaligned positions here. Aligned is nothing but the area covered by the pole here. Unaligned is the area which is with the air gap here. Okay, when the number of poles increases here, the winding area decreases as you see in the diagram here. And second thing is, as the winding area is very less here, as we have more number of poles here, there is a small difference between the aligned and unaligned positions of rotor, so that the inductance will also variations of inductance will also be very less here, and increasing switching frequency here. Okay, so when more number of poles are there, more switching frequency will be there, and losses will also be generating here. And suitable, and this type of mainly suitable for lower speed here. Okay, applications for direct EV applications. Mainly we are all discussing this mainly for EV vehicles here. Coming to the next one here, outer rotor switch reluctance motor in wheel drives here. So here just now I discussed earlier here. So I am using this for in wheel or motor control here. That is, I am directly placing the same in the motor here. So here you can see that what is the name is specified as outer rotor. That means rotor is placed outer side and stator is placed inside here. So just let's try to have a clarity here. Yellow color is the rotor in the previous case where it is placed inside, and pink color is stator where it is placed outside here. Okay, where it is placed outside here, Okay, now here in the other type here, so ultimately I need to have conductor, magnetic field, and relative motion, current carrying conductor is placed on the magnetic field, and a torque is generated. Similarly here I am placing the rotor outside here, and the rotor is placed outside, and stator is placed inside. Okay, stator is placed inside. Okay, so what are the advantages with this condition? Ultimately torque is going to be generated. Okay, torque is going to be generated here. With this kind the advantages will be, so here robustness will be there here. That means, and it is much more, it's similar to the induction motor, which is very robust, and it can be operated in anywhere here, and in different conditions also. And heat tolerance, it can able to withstand with higher values of heat also, and flexible in shape here. And direct drive eliminates the need of gearbox. As I just told that, as I am directly placing this kind of arrangement in the wheel here, if this is a wheel here and at the center, I can able to place this motor directly in the wheel with the wheel point, and this will be the supporting one here. Okay, normally this is what we see here. So this portion will be okay, this portion will be motor here. As I'm using this combination here, okay, there is no need of a gearbox, separate gearbox, so that transmission losses will be reduced here. Okay, so design consideration here. Major, what is the drawback here? The rotor diameter will be increased here. Just now we see the diameter of the rotor is very high here. More rotor poles than the stator poles to minimize the torque ripple. In the previous case we have discussed that number of stator poles are more than the rotor poles. Here torque ripple is more. Now here when the rotor poles are greater than stator poles, then what happens here? Then torque ripple can be reduced. Here. Okay, torque ripple can be reduced. Okay, I'm just changing this. So yeah, this is just now this is clear explanation here. Rotor is yellow in color shape, stator is purple, and windings are placed in blue color here. Outer rotor configuration diameter is larger than the stators here, which is the main characteristic here. So the major points to be considered here, it is suitability for in-wheel drives here. Just now I discussed that, and elimination of reduction gear here, which is also discussed now here. Rotor pole count here. Here there are more poles compared to the stator here. With this here torque ripple can be reduced here. And what is the shape here? It is in pancake shaped design here. Okay, it is in pancake shape because it has a larger radial diameter and shorter axial length here. It's similar to this somewhere in cylindrical salient type here. So when salient type is the diameter is more and axial length is less here. So it is, you can say that diameter is very, very higher than the axial length. So if you can recollect the synchronous machines. Okay, so and coming to this principle of SR motors, we'll try to discuss quickly, have a discussion of this SR motors here. So what I'm trying to do here, I'm having three pole pairs here: A dash, A dash, B dash, A dash, B dash, C here. So what I'll try to do here, I will try to energize each phase separately here. So it will follow the minimum reluctance path here. Whenever reluctance, that is, which is denoted with S here, so it is analogous to resistance term here. So as current always flows to the minimum resistance path here, similarly flux also flows to the minimum reluctance path here. Okay, so I'll try to provide a minimum reluctance path by energizing certain pole pairs here. So initially what I will try to do here, I will try to energize A phase. Okay, then automatically what happens here, rotor poles are attracted to the stator poles of phase here, so that rotor pole slightly tilts, rotor pole shifts here to the A phase here. So automatically there is a minimum reluctance path is generated here, so that it will shift to the rotor poles will be shifted towards the just A dash here. Once it is shifted here, again I will try to disconnect this. Why it is shifting here is because of the minimum reluctance path here. Once it is shifted here, the A phase is de-energized, and again I am trying to energize the next phase here, that is equal to B phase here. Now when B phase is energized here, okay, so then when B phase is energized, okay, let's assume that, okay, when the B phase is energized, again the rotor try to shift here. Okay, we'll try to follow a particular sequence so that the rotor continues to rotate here. In this manner the rotor starts rotating here. Ultimately it will follow the minimum reluctance path here. How to change the direction of rotation here? So by reversing the change sequence of excitation, instead of ABC, which I done now here, instead of ABC, if I interchange the phase sequence or sequence of excitation, then the rotor position will be changed here. And rotor position feedback here, in order to get the accurate rotor position here, so we need to have correct switching sequence has to be done properly here. So what is switching frequency here? The number of poles, rotor poles directly influences the switching frequency here. So the more the number of poles here, then what happens here, higher switching frequency will be required here, because more number of, just now we see that